Angular momentum and orbital mechanics. Linear momentum, angular momentum. What is momentum anyways? Let's just read the definition out of the dictionary. So momentum is the property or tendency of a moving object to just keep moving. So here's this guy on a bike and he just keeps moving. This comes from Newton's first law. An object in motion wants to stay in motion. Object at rest wants to stay at rest. That was originally published in the Principia. Here's the English of it. Every body persists in a state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. Okay. Now, objects on Earth tend to stop moving pretty quickly because there's air drag and friction and all kinds of non-ideal sources to suck away your energy. So let's imagine somebody in outer space where there's no forces, there's no friction, there's no air drag. If this guy has some velocity and he's just floating with some velocity, he's going to keep with that velocity, keep going, same direction, until some force changes his velocity. Now this is talking about translational motion, so just going in a straight line. What about if this guy in outer space was rotating somehow? This continue moving, would this apply to rotational motion as well as translational motion? What do you think? Is he going to just keep rotating and keep rotating and keep rotating? And what would stop him from rotating out here? Just like he would keep moving, and what would stop him from moving? So I'm going to change Newton's first law. I'm going to get rid of moving uniformly straight forward, because it's more than just going straight forward. It's any kind of motion. It's straight forward motion, it's rotational motion, it can even be vibrational motion. It's going to keep doing what it's doing until a force stops it. The velocity can be changed by a force. How would we change translational motion? So you just have some opposing force, and that's going to change what the velocity is. How would we change rotational motion? If we just pushed on the center of him, he might still rotate. For rotational motion, you have to go back to concepts about moment, R cross F. So it's not just a force to stop rotational motion. You have to get a radius there and have a moment that's going to stop or change rotational motion. Two types of momentum. Linear momentum, talking about linear motion. There's also angular momentum that's stopping rotational motion, or looking at conservation of rotational motion. L equals mv, h equals r cross mv. Think back and see if there's anything familiar about this. Is there any relationship between mass times velocity and mass times acceleration? R cross mv versus r cross ma. There's some kind of similarity between these guys, right? So let's look at this a little bit further. F equals ma. There's Newton's second law. Change that acceleration for change in velocity over change in time. Rearrange terms, take the time over, and we see f dt is what is going to change m times v. If we integrate this, so we have v2 minus v1, or take the v1 over here, some initial velocity is happening, and then you're going to apply a force to it through a time period, and that's going to change that velocity to some second velocity. Now, if no force is applied to the system, the initial velocity is the same as the second velocity, nothing changes, and we would call that conservation of linear momentum. Velocities are not changing. So if there's no force applied, the velocities, it's just going to keep floating and floating in the same direction with nothing changes. So that's the linear case. Let's look at the angular case. For the angular case, we're going to start out with a moment. So moment is r cross f, r cross ma. Once again, we're going to replace our acceleration with dv dt. Rearrange some terms. So this time, instead of force dt, we have moment through a time period. And if you apply a moment through some time, you will be able to change that rotational motion. So how fast it's originally rotating, r cross mv, and then you apply some kind of a moment to it, and then you have the final rotational velocity. And in this case, if you don't apply a force, if you don't apply a moment, then that rotational motion initially is going to be the same as the initial rotation finally. And realize this is a cross product, so it's not just applying any random force. To change rotational motion, you have to take that force and apply it at some distance away. Okay, so it's r cross f, where the force has to be some distance from the axis of rotation, and that is what's going to change that rotational motion. And if there's no force acting with this cross product, angular momentum will be conserved. So no m dt, initial rotation will be the same as the final rotation. Let me just review moments, and this is going to feed into orbital motion. We have a bolt over here and a wrench and a force applied over here. If you remember from moments, part of this force, this x component, it's not going to rotate anything. It's just pushing on the bolt. The piece of the force that rotates it, it has to be perpendicular. That was the thing with the cross products, that you would take a force, and the whole point was to find the perpendicular part of the force, because that's what was going to rotate it. This is also the part that's going to change rotational motion. Okay, so we're looking for cross products and the perpendicular piece of that force. Let's apply this to a system where we have the sun is in the middle, and we have a planet that's rotating around here. And think about what forces are acting on this planet. If you drew a free body diagram of the forces acting on this planet, what would it be? If there was some random force in this direction, just like the previous example, part of that force would push and pull, but this would not change rotational motion. Okay, this is just pushing and pulling on it. The only way to change rotational motion is if you have a perpendicular force on this system. Let's take this away, and what does gravity do? Gravity is pointing straight towards the sun. Okay, so this is pushing and pulling, but gravity is not going to change the rotational motion because it's not perpendicular to what it's rotating around. It's in the same radial direction. If we wanted to change the rotational angular momentum of this object, we'd have to get a force that was perpendicular to that lever arm. Okay, so if we got a rocket ship out and started pushing on it at this way, then that would change the angular momentum. But gravity is not perpendicular. Gravity will not change the angular momentum. So this is centralized forces don't change rotational motion. Gravity is an interesting quantity, and we don't understand everything about it, but apparently matter has a property that attracts one another. Let's call this capital M for a big mass of the sun, and then over here is a little mass of the planet. And Newton found this universal gravitational constant that seems to work through the universe, 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. And that relates kind of this attraction between the sun and the planet, and it's inversely proportional to the square of the radius. So as the radius gets larger, that gravitational constant gets smaller. If we cancel out the m's here, so here is gravity. If we are on the Earth, that would be the radius of the Earth and the mass of the Earth. If we're on Mars, and we'd use the mass of Mars and the radius of Mars, but it would be that same universal gravitational constant to calculate how much we're kind of getting sucked into that large mass underneath us. Okay, so F equals mg, and this can also be g_mm over r squared, where r is the distance between the centers of these two pieces of matter that are attracting one another. Let's go ahead and get back to Newton's second law, where we're going to add up all the forces on something, and if those forces don't add to zero, they will describe how the object is accelerating. Okay, statics problem. If you drew a free body diagram of this planet, what forces are acting on it? We have just the void of space out here, no air drag, nothing at all. The only force acting on this guy is gravity that's pulling it towards the sun. Okay, so that's the forces, and obviously this is not balanced. We have a big force going to the left, and there's nothing pushing it back to the right. So just a lopsided, unbalanced force that's pulling it to the left. Now let's think about how this force translates into what accelerations are happening with this orbital motion. So here's our force of gravity pulling to the left, and that means we are going to have an acceleration to the left as well. Okay, force to the left adds to acceleration to the left. And if you remember what you know about rotational motion, there was two pieces of acceleration to that rotational motion. There was the translational piece, so if you changed the magnitude of the velocity, so if you start going faster and faster or slower and slower, that would be that velocity magnitude change. And then the other piece of acceleration was v squared over r. That's the piece that describes changing the direction of the motion. And that is what is happening for orbits. Okay? So what the planet wants to do, it wants to go shooting off in a straight line. It doesn't want a curve. But instead of shooting off in a straight line, the direction of it is changing. It's getting sucked back into the center because of that gravity. So this is the direction change that this mg creates. So it's not changing the magnitude of the velocity, but it is changing the direction of the planet. So our acceleration here is v squared over r, and this comes from changing the direction. Go ahead and review those rotational accelerations if this is not looking familiar to you. One more thing we can add here. So here's our forces adding to our acceleration. Our force, we can plug in that universal gravitational constant, our masses, the radius between the planets. So here's that gravitational force between the planets, and this is adding together to the acceleration that's changing the direction. So the v squared over r chunk of our circular acceleration. Now m is the same on each side, so I'm going to cancel out that little m. V squared, so let's put a square root over here, and we can get an equation showing what velocity we need to just balance the gravity pulling in. So if we choose just the right velocity, we'll end up with a perfectly circular orbit where that direction change, v squared over r, is perfectly supplied by the amount of gravity at that radius. So again, forces are equal to the acceleration that is created. Here's a nice, perfectly circular orbit. So the planet wants to go flying off in a straight line, but the velocity is just perfect so that the gravity pulling in matches that mv squared over r. And that will keep a constant radius through the entire orbit. Let's play the what if game. What if our velocity is smaller than it needs to be to keep that circular orbit? So if the velocity is not quite large enough, it's going to fall into a smaller orbit. It ends up falling into kind of this elliptical orbit. So instead of staying up here at the circle, it will fall down here and do one of these things. Play around with that simulation that shows the orbiting planets, and you can start with a circular orbit, bump the velocity down, and you'll see this new orbit created when you bump that velocity down. What would happen if your velocity is too large? So if it's too large, it'll almost go flying off in a straight line, right? So the gravity is not quite pulling it back. So it's going to have this larger orbit, but eventually it will come back, okay, unless you hit the escape velocity. So you're still going to have some kind of an orbit. It's just going to be this large elliptical orbit. We're going to be coming away off of that circular orbit on the other side in this case. How can we use this? How can we play around with our velocities to play around with what orbits we're in? Let's say we're starting out at a small orbit right here, but we don't want to be this close. We want to be out here somewhere instead. How can we go from this inner orbit to this outer orbit? Okay, so we're going around in a circle. Our velocity is perfectly balanced. What are we going to have to do to get out to the edge? Well, if we pop our velocity up a little bit, we're going to escape that circular orbit, but now we're in this elliptical orbit, right? So we're still coming back to that original spot we were in. So we're going to have to do one more thing out here to reach that circular orbit. See how when we're far away, our velocity's not large enough, so we keep falling back into that smaller radius. So what we're going to have to do here is bump our velocity up again. And we can look at the radius we want, and we can bump our velocity to perfectly match that new circular orbit that we want. So our first radius, and then speed up a little bit, and then speed up a little bit more. So you can play around with what velocities you have if you want to change around what orbit you're in. How does this tie into conservation of angular momentum? So let's get that conservation of angular momentum equations out again. We found that in order to change rotational motion, we were going to have to apply a force. That force for rotational motion is a moment, so r cross ma or r cross m dv dt. So a moment applied through some period of time, that is what's going to cause this r cross mv to change. Okay? Gravity is not perpendicular to our lever arm, so gravity does not change the orbits, and we should have an initial radius and velocity is the same as a final radius velocity. Okay, so if we have some big radius and a little velocity on one side, so big R1, small V1, we're going slow way out here at this large radius. And if we happen to be in one of these elliptical orbits, by the time we get around to the other side, if we haven't applied any external forces, we're just flying around in space. There's no air drag, there's no weird forces out here. We're just going infinitely around and around and around, no forces to change this. So our moment goes away, and that original cross product, r cross mv1, is going to be what we are on the other side too. So we have a short radius, which means now we're going to have a large velocity. So short radius, large velocity, large radius, short velocity. This is conservation of angular momentum. Same thing as if you're, ice skating and you pull your arms in when you're ice skating and you go faster. Smaller radius, faster velocity. Or if you throw your arms out bigger radius, slower velocity. And you can play around with this on that simulation too, where you'll see it go. It'll whip around really fast at this small radius, and then it'll slow down out here, and then it'll go faster and faster. But the overall R cross MV, that's conserved. What if we're not at the apogee or the perigee of this thing? What if we're at some random position? This R cross MV, it's a cross product. Just like our moment, R cross MA, R cross MV. So if we're over here where our velocity is not perpendicular to that position vector, so now our velocity is at some other, we're still going to be tangent to that curve. But what we're going to have to do out here is break our velocity into how much of it is perpendicular to our radius. And this perpendicular chunk, that's the piece that is conserved. So what's not perpendicular, that doesn't go into the cross product. We're just concerned with how much of our velocity is perpendicular to our radius, and that's the piece that is going to be conserved with this cross product. So we have F equals ma, moment equals R cross F. We played around with moving dt's around. And this is kind of a sneak peek for what you're going to see in some future chapters too. So for chapter 12, we got rid of impulse. Force acting through a time period, that's called impulse. And in the future chapters, we will add a force through a time and watch how that force actually changes the velocity. But for now, we're not worrying about applied forces. So our initial and final velocities are going to be the same. And you can look at it as conservation of linear momentum, or in the case of rotational motion where we have moments acting, if a moment is not applied to it, then initially R cross MV is going to be the same as at the end, R cross MV. And if you can do cross products for forces, it's the same idea doing cross products for velocities. So it's the same idea in each of those cases. And if there's no external moment that is applied, our initial R cross MV is going to be the same as our final R cross MV, and we call that conservation of angular momentum. So our momentum, MV, angular momentum, that's at R cross MV. This is a rotational piece of it. And that's going to be conserved if we don't have any external forces that are changing the thing around. Hope that helped.